Again, it's a rich thing.
What is going on, guys? Welcome back to the C programming tutorial series for beginners. In today's video we're going to talk about pointers, so let us get right into it. Alright, so let us talk about pointers in C. And pointers are actually quite simple to understand once you understand how memory addresses work. And we talked about memory addresses already when we talked about arrays. Essentially, we have the random access memory of the computer, so the RAM, and we have individual slots. And these slots, we're going to say now, are 1 byte. So each of these slots is 1 byte, 8-bit. And as we know, using this compiler, using this system, an integer takes up 4 bytes. So this here would be the space that one integer needs, 4 bytes. And each of these slots here has a certain memory address. We can now, for the sake of simplicity, say this is 0x0, 0x1, 0x2, and so on, 3, 4, 5, 6, 7, and so on. And then we go to 9, A, B, C, D, E, F, so hexadecimal numbers here. But essentially we have these memory addresses here. So this integer stored at this location here would have the memory address 0x0 because that is where the memory address starts, and it has 4 bytes. The next integer, if it's in the neighboring memory space, so if we have another integer here, would also take up 4 bytes and would have the memory address 0x4 in this case. So this is how basically memory addresses work. Now, in order to get these values in C, what we need to do is we need to create such a variable. So for example, int a equals 10, and then we can use the addressing operator or the pointer operator, the referencing operator, to print the actual memory address. So I can say printf, and now %p for pointer, \n, and then we can pass int a. Now remember, this end symbol here, this operator here, was used already when we wanted to scan something. So when we wanted to take the user input and scan it into a variable, we used that to indicate that we're actually targeting not the variable itself, but the memory address of this variable. So in this case, we can run this, we can compile this, gcc main.c main. And when I now run this, we're going to see a memory address. So this is just one address. But what you're going to notice here is that when I create a second integer with the value 20, for example, and I copy this line, and I also print the memory address of B, you're going to see that it's almost the same, but it's 4 bytes after this one. So you can see basically what we did with 0x0, 0x1, and so on. Here we have it in a different memory space. So this is where we are at, and this is the first one. 4 bytes later we have this one, and so on and so forth. If I now choose to create a character instead of an integer, so char c equals a, for example, and then I print the address of c. Now in this case we won't actually see what I'm talking about, but if I create another integer here, so int d equals 20, for example, again, then I print this as well, you're going to see that there's a difference between integers and characters. So when I run this here, you can see from C to 0, this is a jump of 4 because we have C, then we have D, E, F, and then we have 0. So this is a difference of 4. Actually, we see that C is doing something else in the background here. So we can see that actually, in order to fit this more beautifully into the memory, C has repositioned the allocation. So you can see actually that the character is allocated first, but nevertheless, you can see that after the character, 1 byte after that, the integer starts. So we don't have the order as I expected it here. Because we don't have first the integer, then the next integer, then the character, and then another integer. We have the character first and then 3 integers, but the point that I wanted to make is still here because we have this character here at this address, and then 1 byte later, so from B to C it's just 1 byte, we have the integer. This is because a character occupies 1 byte. So this is how you can look at the memory addresses, but those are not pointers yet. Those are just memory addresses. A pointer is a variable or an object that points to the memory address of something. So for example, we can have an integer pointer. We can call this int my pointer. And then we add this star symbol here, this pointer symbol or pointer operator, you could say. And usually I like to do it here. Or actually, I think we need to do it there. So we have an integer pointer to the memory address of A. This is now a variable. So we can go ahead now and say printf %p \n of my pointer, and we're going to get the same result here. There you go. So you can see, of course, different memory address and all that, but this is now an entity or a thing that points to the memory address of A. Now, I can also try and print this as a number, but you can see here that I get the warning that I'm trying to print an integer even though I'm passing a pointer. Not even sure if this is going to run properly. Okay, we get something here. But what we can do is we can dereference a pointer. So a pointer has the memory address, but we can also dereference the pointer, so we can try to get the value of the thing that is that this pointer is pointing to, because this pointer is pointing to the memory address of A. So the value of the pointer is the memory address of A, but I can dereference the pointer to get the value that is stored at the memory address of A. And I can do that by just using this same operator here, the star symbol, to dereference the pointer. And in this case, this gives me an integer. And you can see that I get 10 as a result. So this is how pointers essentially work. We can also use that dereferencing here to change the value of A. So I can go ahead and say my pointer. First of all, if I just do my pointer something, it has to be another address. So I have to pass here another memory address, but I can also dereference here. So I can say my pointer dereferenced equals 20. And then I can just go ahead and say printf %d \n A. So I'm not even printing the pointer, I'm printing A. And you can see that this changes the value of A. So this operation here, this means that we're changing the content at the memory address, whatever. And this memory address, whatever, is the memory address of A, and we change it to 20. Then we print A, and we can see that A, in fact, has the value 20 here. We cannot do that with an ordinary variable. So I cannot just say int copy equals A, and then copy equals, I don't know, 300, and then printf A. This is not going to work. So making a copy is not the same thing as using a pointer, dereferencing it, and changing the content of the memory address. So this is a difference. This is something that you cannot do just with basic copies. Now, one thing that I want to show you here is the size of a pointer, because the size of a pointer can be printed here again with %ld \n, then size of my pointer, the actual pointer. And you can see that in this case here, it has 8 bytes. So the size of a pointer has 8 bytes. Why does it have 8 bytes? It doesn't have 8 bytes because the pointer is so complicated. It has 8 bytes because we're operating on a 64-bit system. On a 64-bit system, the memory addresses have 64-bit, aka 8 bytes. So 64 divided by 8 is 8. So we have 8 bytes. On a 32-bit system, we should have 4 bytes for a pointer. So the size of a pointer is going to be 8 bytes just because the memory address space is 64-bit. So this is important. What else can we do here? We can also, of course, this is important. I didn't mention this here. The pointer itself, of course, is also stored in the memory. The pointer is not just some magical thing floating around in the code. It's actually another thing stored in the memory. So actually, we can print a couple of things here. We can print the address that the pointer is pointing to. So we can do that, which I actually did above, but I can also print the memory address of the pointer itself. So you can see that the pointer itself is stored in the memory, and of course this means that we can create pointers. We can create pointers that point to pointers. So we can go ahead and say int and then star pptr, so pointer basically, equals end my pointer. And this then creates a pointer that points to the memory address of the pointer. Now, don't be confused here. This is all very abstract. You cannot see right now why this is relevant or important, but this is how we work in C. We have to do this manually because it depends. It is oftentimes important what we actually pass. Are we passing a pointer? Are we passing a variable, a copy? we need to know about that stuff. In Python, we do not know about that stuff because it's not really relevant to us. In Java also, we don't know about that stuff. Java works with pointers, but we don't see the pointers. In C, we need to actually care about this. So here I can pass again pptr, which is a pointer to the pointer. And guess what? We're not going to do this endlessly here, but this thing here is again stored in the memory, so we can point to it as well. We can do this over and over again. We can point to pointers of pointers of pointers and so on. But we can also dereference the pointer, and it's still going to be a pointer because it is the pointer my pointer. And then, last but not least, we can also get the value by dereferencing it twice. So we can dereference the pointer and then dereference the pointer that the pointer pointed to. It's getting more and more complicated here, isn't it? So there you go. You can see what I'm talking about here. Again, this is just some theoretical background here. You don't need to understand everything exactly and why you need it. Essentially, we have things in C that allow us to store the memory addresses of objects, and we can use those to actually pass the precise pointers, the precise addresses, which is important because sometimes we have functions like the scanf function, and we can only pass references or pointers and not just variables, because variables have values and pointers have memory addresses that we can change. And one thing that is also interesting to notice here is that arrays essentially can be treated as some sort of pointer. So an array is essentially just a pointer to the first position. So if we have, for example, an array, an integer array with, let's say, 100, there you go, with 100 values here, this array is essentially just a pointer. So I can go ahead and say printf %, p \n, and I just have to pass the array. I don't even have to pass the end symbol here. With every other variable, if I have, for example, here, I don't know, a floating point number, f, and I want to print a pointer here, I cannot just pass f, right? This doesn't work because that is not a pointer. But array itself is a pointer, so this works here. You can see that this is the address of the starting element. So essentially, we can use that to get the beginning memory address. So an array itself is just the address of the beginning of the whole thing. Because an array, we have here an array with a couple of slots here. Let's say all of these are 4 bytes because it is an integer array. This here is index 0, and if we get the pointer of an array, we get the address of the first position, basically. We can also go ahead and actually just print the pointer of a certain position. So we can go ahead and say and array 56, for example, and then we're going to get the memory address of that particular position. And here I'm not going to do the calculation right now, but this should be 56 times 4 bytes after this address here. So that should be the difference. Just a nice thing to know on the side that arrays are actually just pointers. This can be important when programming. Besides that, we should also talk about pointer arithmetics. Pointer arithmetics are actually quite interesting because once we have a pointer, again, let's create a variable a equals 10. We can create a pointer here, and ptr is going to point to a. We can also go ahead and do pointer arithmetics. A pointer can be increased, a pointer can be multiplied, and so on. So essentially, I can go ahead here and say printf %d \n, and I can dereference the pointer here to get the actual value of a. And then I can also go ahead and create another variable b equals 20, and I can say ptr++ without dereferencing, so I'm not actually increasing the a by 1. I'm increasing the value of the pointer by 1. Increasing the value of the pointer means jumping one space or one memory address space to the right if you want, so to the next area, which means in terms of an integer, adding 4 bytes. If you're not dealing with integers, if you're dealing with characters, this is 1 byte, at least with this compiler and this system. So if I actually go ahead and copy this, I think at least that I should get, yeah, there you go, b as a result here. So I just changed the pointer here by increasing it, and then I dereferenced it and got the result. Now if I add c here, I can also print it directly. So I can say, okay, get the pointer plus plus the pointer. So increase the pointer by 1, then dereference it, and this should give us 30 here, as you can see. So that's essentially the basic idea behind increasing pointers. We jump one address. I can also do this right away, so we can actually do plus equals 2 here. This is not going to increase the pointer by 2. It's going to increase the pointer by 8. So it's not going to jump 2 bytes. It's going to jump 8 bytes, so two times an integer size. There you go. So we skip the 20 and we jump immediately to the 30, since it's in the neighboring memory space. And of course, we can use all that to also jump back. So I can say pointer minus minus. I can then print it again, and then we should see 20 afterwards. So a very simple thing. This is how we can jump with pointers, how we can increase them, decrease them, and so on. We can, of course, also go out of the memory space. So I can say plus equals 8. And if my program does not crash, we're going to get some random values here. I can also change this to 15 maybe. I don't know. Maybe we're going to encounter some interesting values here. The problem is when you choose to write, because, you know, now I jumped with a pointer to some memory address. I don't know what's there. And if I then go ahead, dereference it, and assign something to it, we don't know what happens. Best case, the whole application crashes, and that's it. Worst case, I do something that I don't even realize I did, especially if this is a serious tool. I have created some severe security issue here, so this is something that you should definitely avoid. Remember, in C, you can go out of the targeted memory space. You can do whatever you want. You can overwrite jump back addresses, which makes it, of course, very vulnerable to buffer overflow attacks. So you don't want to do that. But this is essentially how we do pointer arithmetics. That's that. So then we also have, how can we basically iterate via arrays? So this goes back to the point that arrays are essentially just pointers to the first position. We can have, for example, int numbers 100, and then I can just say, okay, the first number, the pointer to the first position, is essentially just numbers itself. And then we can do a for loop. We can say for int I equals 0, I is less than 100, I plus plus. There you go. And here we can then set the value. So we can say, take the position of the first number, add I to it, so jump I positions, dereference that thing, and add something to it. For example, I times 20, I don't know. So again, we take the first position always stays the same. We add I to it, which means that we jump in the first iteration nothing. We stay at the first position. In the next, we jump 4 bytes, then we jump 8 bytes, 12 bytes, and so on. And we always set another value. And then we can also go ahead and print these values with another loop. So for int I equals 0, I being less than 100, I plus plus. We can just print f%d \n of numbers I. What's the problem here? Oh, there you go. Compile, run, and you can see the values here. So this is how you can do that. Then a couple of things we should talk about is something called the null value. I'm not sure if we discussed the null value already. I think not. Null is essentially just, in C, it's just a macro or a constant that represents 0. In other languages, null stands for basically nothing is here. And in C, it should also stand for that. But the practical thing is, or the reality is, that null is essentially just 0. So if you say, for example, here, integer pointer points to null, this basically, you do that to say, okay, this pointer points nowhere. However, null is essentially just another way of saying 0. So this is basically the same. I think that the only difference is that it's somehow turned into a void pointer. I think it's typecasted to a void pointer, but essentially it's just a 0. In C, in C++, we have the null PTR, which works a little bit differently, but we don't have objects and so on in C. Speaking of void pointers, we can use void pointers to keep the data type of the thing that we point to flexible. So we can say void pointer VP here is, for example, the pointer to A. We don't have A. A could be an integer. So this definitely works. But we can also point to different things, right? So we can point with a void pointer to essentially everything. And then we can also print this. So if I say printf d \n, and if I now want to dereference the pointer, we have to do that using typecasting. So I would have to do it like that. And then, or actually, did I do it? Oh, sorry. We need to typecast first into an integer pointer, and then we need to dereference it to work. But this is how you would do that. Can be quite useful, but we don't need this for this beginner level that we're at right now. So this is just something that, you know, you should maybe know that is possible. Another thing is that I think this is an interesting thing. If we have something like a character pointer, and this character is, or a character actually, and this character is A, and then we want to print the pointer to C, I think, was it like that? I think in C we actually don't have the issue that much, but in C++ we have the issue because we can also interpret this as a string. That's the problem here, because essentially what a string is, we already talked about this, a string is an array of characters. And an array of characters, as we already talked about this, is essentially just a pointer to the first position. So if I say that the pointer to C has to be interpreted as a string, essentially this is going to treat and C as a string, as a character array, and it's going to look for the null terminator and just print. So this is just also one thing to know. This episode is quite theoretical. We learn a lot, we don't really do a lot, but this is something that you always need to keep in mind when you work with things in C. And the last thing that I want to show you for today's video is how we can work with function pointers. So we have basically a pointer to a function. Let's say we have, let's define a function here. Void my function. Actually, let me do it like in my example here. Let me call them function1. And we're going to print with function1 \n. Then we're going to copy this. We're going to paste this function2. And now we can use a void pointer to keep it flexible, which one we're actually selecting. And then we can just execute the void pointer. And depending on the variable, we can just do that. So we can say void, and then in parentheses, we can use this operator here again and call this my function, for example, like that. And this essentially creates this void function pointer. The important thing is that it has to have the exact same signature. We cannot have multiple parameters here and not have them here. We cannot have a different return value. It has to be the same thing. It has to have the same signature. And the return values, as I said, have to have the same data type as well. And then what we can do is we can say my function equals, and we can pass function1 here without calling it, just referring to it. And this now, if I say my function, call this calls function1, even though I call my function. If I choose, however, to say my function equals function2, this will execute function2. And I can change that, right? So I can first execute function1, then change and execute function2. And this is one thing that you can do with void function pointers. So that's it for today's video. Hope you enjoyed and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe and hit the notification bell to not miss a single future video for free. Other than that, thank you very much for watching. See you in the next video, and bye.